So today let's talk about one of the most interesting things that revived itself after a decade, remote procedure calls, fondly called as RPCs. They are widely adopted to do inter-service communication over the network. The core highlight that sets RPCs apart is that it is designed to make a network call look just like a local function call. It does this by abstracting out all the complexities like serialization, deserialization and transport. In this video, let's take a look into what RPC is, where does it fit, what are stubs, how communication happens between the services, and conclude with going through the advantages and disadvantages of using RPCs. But before we move forward, I want to talk to you about a code-based course on system design that I have been running since March 2021. Right? If you are looking to learn system design from the first principles, this course is for you. Yeah. Because this is a cohort-based course, it will not just be me rambling a semi-optimized solution thinking it's the most amazing solution out there. Instead, it will be a collaborative environment where every single person who is part of the cohort can pitch in his or her ideas and we will evolve our system around that. Right? Every single problem statement comes with a brainstorming session where we all together brainstorm and evolve our system. That's way everyone understands the kind of trade-offs we made while making that decision. Instead of just saying, hey, we'll use a particular queue, we'll have the justification why we use only that queue, why we use that particular database, why SQL, why not NoSQL, right? How are we leveraging throughput? How are we ensuring that our system scales? That's the highlight of this course. This course is taken by more than 500 engineers to date, spanning 9 countries and 7 cohorts, right? People from all top companies have taken this course and the outline is very intriguing. It's very exciting. So we start with week 1 we start with the core foundation of the course where we design online offline indicator, then we try to design our own medium, then we go into database where we go in depth of database locking and see few very amazing examples of database locking in action and how do we ensure that our system scales through that. Then the third week is all about going distributed where we design our load balancer. I'll walk you through the actual code of a toy load balancer and understand how TCP connections are managed and how simple it is to build load balancer. Then week 4 is all about social networks. Week 5 is all about building your own storage engines. Like we'll build that intuition on if you were to ever design your storage engine, how would you do that, right? Then week 6 is about building high throughput systems. 7 is about building IR systems, basically information retrieval systems and ad hoc designs where we design our own message brokers like SQS where we design distributed task scheduler. And we conclude the course with week 8 where we talk about the super clever algorithms that has powered or that has made those systems possible, right? I have also attached a video verbatim as is from my first cohort where we designed and scaled Instagram notifications. I will highly encourage you to check this video out, right? And now back to the video. So say we have 2 services and they want to talk to each other. One acts as the client, another one acts as the server. And the most standard way to do this communication is when your client needs something, it makes a request to the server and server responds back, right? And this happens over any communication protocol like let's say TCP, UDP, pick your favorite, right? This is not RPC. This is not RPC specific instead. Like this design is a very common way through which 2 components in the network will talk to each other, right? And this is how the entire distributed system is built, right? So then what's that makes RPC different? So let me give you an example. Let's say when you are writing an application, you have an authentication service and you have a notification service. So authentication service, whenever someone tries to log in, you want to send that user an OTP. OTP sending is handled by the notification service. So now what needs to happen is that your authentication service needs to talk to the notification service. How will this communication happen? Right. So this is where RPC come into the picture. So in order to understand or in order to see how beautiful RPC is, let's take a look into the code of it. Like how would you write the code to do this? So your login method would look something like this. Def login, you take email and password, you write your basic code to generate access token, and at the end you put in notification underscore OTP in brackets email. So send an email OTP to this particular user, right? So this is how you would write the code, but how will you implement the notification underscore OTP method is where the magic happens. So for example, if you are using REST, like the most common way to do any communication right now is REST, right? Where what you will do, that you will write the function notification underscore OTP that would make an HTTP call, which is a REST based HTTP call to the notification service on the endpoint which is exposed by that service, right? For example, if that service is running on host or with a domain name notification.abc.internal, you would make HTTP colon / notification.abc.internal /email /OTP, and then you will pass in the email ID there to send the OTP. Right. Now here is that what's the problem here? Like everyone would do that, right? But what's the problem? The core problem here is, now this is not just one API call. Your service might be interacting with 50 other services, and you would have to write that same thing again and again. What? Making that HTTP call, right? For example, if you are using Python, you will use, hypothetically, let's say you are using request library, right? So at every place you are making that request library call. Like with a better low level practice, you would be abstracting few things out, but still you would have to write that particular piece of Python code to invoke that HTTP API and then get the response. Now, apart from that, you would also have to handle cases like, for example, what if your network is unreliable and your request fails, or you need to do retry, or your client is down, or your server is down, and then you would have to do that retry, handle failures, send error message to the user, do exponential backup, whatnot, right? So here, and this is just the login service that has to do all of this in order to talk to notification service. Let's say there is recommendation service who also wants to talk to notification service. It also needs to do these exact same things. The worst thing that would happen over here is, let's say one service is written in Golang, another one is written in Java, third one is written in Python. Every language has its own way of talking HTTP with other service. Like for example, Python has request library, Java is something else, Golang has net/HTTP package. So there is no standardization, right? So this is what brings out as a problem to be addressed. Why is there no standardized way to talk to establish communication between two services? Why do every single one has to write everything from scratch and like handle all of these things unnecessarily? Like this could well be abstracted. Why can't there be a standard to do so? Which is where RPC comes into the picture. So what if we abstract out the repetitive and mundane tasks like communication protocol? I don't want to use TCP, I want to use, let's say, UDP. But when someone says, no, I want to use TCP but with HTTP 1.1 or TCP with HTTP 1.2, there is so many choices to make, right? So what if we abstract out this repetitive task, or repetitive and mundane task to be honest, like communication protocol, object creation, failures, retries. Then when you are sending payload, you might want to compress it. You would want to support continuous streaming of requests. When you are uploading large files more than a GB, you would want to stream and not make individual HTTP requests. So many things to take care of. Why can't there be one solution that abstracts these things out and let us, the developers, focus on writing the actual business logic? This is how RPC was conceptualized. So RPC is the way to standardize the communication between services, no matter which language are you using, no matter how you are invoking, what your ecosystem is, it's all uniform, right? That's the best part. So the code that we just saw, def login email password, wrote the access token code, and then you wrote notification underscore OTP email. Now this notification underscore OTP bracket email, when you pass in email to send notification to a user, this looks like a normal function call, right? Earlier we thought of implementing it with Python request library, making an HTTP call and all. But what if this itself is a network call? It looks like a local function call, but internally it hides the complexity of making a remote network call, right? This is exactly what RPC is all about, right? So it makes our code so beautiful that you feel like making a local network call, if you're using an ID, you can do that same sort of autocomplete, like you are interacting with native objects. We'll go into detail of it, like what I mean by that in case you don't understand. We'll go through that. But it makes your function call so native that you will feel that it's a local call only. But instead, behind the scene, it has abstracted out the complexities and made it a network call handling all sorts of optimization and performance bottleneck. Right? So what looks like to you as a local call, in reality, it is actually a network call that happens over the network. Right? And here, it basically is there to hide the complexity of remote call. We should not be even worrying how that call happens. It just happens. Right? So RPCs, obviously, because it's a network call, it is magnitude slower than local procedure calls, but you don't feel like that. Well, actually, that's one of the concerns of using RPC, where if you don't know that this is an RPC call, then and you are invoking it bluntly, you might shoot up your response time. You just need to be aware that, hey, this is the RPC call, but this is the local procedure call. So just be aware when you are using it. And what it actually abstract out for us is RPC abstract out marshalling. Like for example, when you are invoking the function notification_OTP and pass in email into this, someone needs to take, email is what I want to send to this server, and that server need to understand that, hey, notification_OTP is the method called on your end, give me the response back. Right? So who does this? RPC manages this for us. So marshalling, unmarshalling, network packet movement, everything is abstracted by RPC. But before we jump into what RPC is, let's take a small detour and understand what stub is. Like whenever you'll read about RPC, one thing that you'll always hear the term is stub. It's like stub, like, and obviously it seems like a pretty weird thing to say in a technical context, but that's the terminology that the CS researchers went with. Let me clear these things out, what stubs are. So, login is the function login is on the authentication service, right? Notification_OTP function is on the notification service. Now, this someone needs to convert the information. For example, notification_OTP is the function, email is what is being passed over here. Someone needs to convert this and basically marshal this particular thing into something serializable, send into a format that is understandable by both. Like you have login service, you have notification service, right? And someone invoked the function notification_OTP bracket email, or basically while passing email as an argument, someone needs to take this information and basically create a format out of it which is understandable by the server also, by the notification service also, right? This who does this? The responsibility of this is done by stub. And now it's not just about converting from authentication to notification service format, but also from notification service response to convert it back and give it out as a native object to authentication service. So request and response, the conversion of both is what stub plays that important part here. So the flow here would be, let's say you have the authentication service written in Golang. You have notification service written in Java, right? Authentication service has its own little running RPC runtime. Java has its own little running RPC runtime. So what would happen is, where would stub come into the picture? When in the authentication service, you invoke notification_OTP, this converts, or this, the first thing that it interacts with is the stub. So the stub, what it would do is, it would understand that, hey, notification_OTP is invoked with email being passed as an argument. Let me create a very compressed format so that I can send it over the network to the notification service. Notification service. So stub, once it converts it into a format, it sends it to the notification service. Notification service receives it. There, the stub on the notification service understands what has been sent, and then it converts it into the native object of notification service in Java. So Golang's struct gets converted into Java's class, right? And then once it understands it, it takes the necessary action. Right, now notification service may invoke third-party API to send the email notification or whatnot. We'll not go into that, but assume that notification service is doing its part well. Once it has triggered that OTP, then it would create the response and it would send it back to the authentication service. But how? It would create the response, go to the stub would marshal it into a format, would send it, so that stub in the authentication service understands it, and then it would convert it back. Right? So stub is the one that takes care of converting the method, the request type, the response type into the form that is used by the RPC system. The best part here is that you may create a struct in Golang which says that send notification request, and you define a response format, send notification response, as a struct in Golang. You would define send notification request as a class in Java, send notification response as a class in Java. Now what would happen is you would normally invoke a function call, you would pass in the parameters, create that thing and invoke the function. Internally it would convert it into a network call and go and fire it. There your send notification request struct gets converted into send notification request class in Java, or the object of that in Java. Then you can normally access it how you normally access the object and its property in Java. You do your computation, basically send the OTP and whatnot. You create a response object, right, which is send notification response object. It gets converted, it gets serialized into a stream format that Java object converts it into Golang struct. So for you, it's pretty seamless. You don't really have to think about, hey, now I got a JSON payload, now I want to convert it into an object. Now I got a JSON response, I want to convert it into this kind of response object. You don't have to do that. That is all abstracted out from you, which is where it gives you such a beautiful way to write code that that's the beauty of RPC. It makes your remote procedure call appear local. Right? So, and that's where stubs comes into the picture. Now we'll see what stub, how do we even configure it? So most stubs, the most common way of configuring stubs is, for example, every single RPC implementation, what it would give you is, it would give you a way to define the interface language, right? And this interface language would be where you define the types. For example, send notification request is a type, send notification response is a type. This type needs to be present in Golang struct and in Java classes. So there has to be a common way through which you define this, right? So that is the interface description language. Now every RPC would have its own implementation, but if I take the most famous implementation right now, it's gRPC, and it uses the protobuf format to do so. So what you will do is you will define a common way, right? You will define it in a normal proto file on this is the service, this is the RPC. Let's say I'm invoking a function, or I'm declaring a function power, part of a particular service with type message or with type send notification request, having a particular set of member fields. So imagine, think of it like your class definition, but instead of defining it in a class in a particular language, you define it in a common you define it in a common basically protobuf format. And it's pretty human readable, very simple to do so. And it's more like just declaration. You are not defining what needs to be done. It's just declaring that, hey, this is the interface that both the services would expose and would implement. Right. So what you do as the first step is you write this interface definition in the format or the compiler that the language understands. For example, if you are using gRPC, you will write it in the proto format. Right. Now when we are done writing this, what we do is we then write a server program that implements this interface. So which means, let's say you write, so from the interface definition language, what you actually first do is you run a generator. So what generator would do is the generator would take this proto file or would take this interface definition file and would create a Java code for you. It would not write the business logic, but it would write the necessary piece of components that is required for it to make a network call, do the retry, everything that it would want to it would generate all of them by reading this proto file, or by reading your interface definition. It would create the working Java file, right? And then all you have to do is you just have to implement the functions that you have defined, the functions that have not been implemented, which is, let's say in this case, the power function or the send notification OTP function. Right? You just have to take care of the writing of the business logic. Everything else which is generated as part of the gigantic file that would be generated, that is all generated to take care of you making a request and basically getting a response, failures, retries and whatnot. Right? So now your job is, once you generate the stub, and now this is what the stub is, right? Your stub generator. So these are called stub generators. So from interface definition, you run a stub generator that creates this auto-generated stub that takes care of marshalling, unmarshalling and invoking the network call, right? And now all your job is that on the notification service, because that's the interface, the notification service needs to implement it, and you would write, and then you would generate the same thing on your Golang side or on your authentication service side as well. And now what the beauty here is that the proto format is common. Your Java, then when you run a generator with Java as the output, it would create Java code. When you provide Golang as the output, it would create working Golang code, right? So now this is the beauty of it. So now what would happen is, you have the structs in Golang, send notification request, send notification response as the struct in Golang, and same thing as classes. So now when you're making a call, you can use those things as pretty straightforward local objects, although it would be seamlessly transitioned into a remote call, but you still are only focusing, like you are invoking like a normal function call, right? This is the core idea behind stubs and how it makes things seamless. So the stub generator is the one that does all the magic. You define a common thing in your interface language, pick any, depending on the RPC that you are using, you would pick one, and then with the Go file or with Java, it would be automatically generated, and then you would start using that, right? Okay. So now how does the communication in RPC happen? Here the biggest myth, I talked to a few people and everyone for some reason says, are you using HTTP? Yeah, so then REST. No, like HTTP and REST, they are not synonyms, right? So what RPC says is, RPC anyway, it's a network call, right? Two services or two machines talking to each other will happen over a network. So RPC can use any protocol that it wants to, TCP, UDP, anything. But more importantly than that, it can use any advanced protocol, like any layer 7 protocol, like HTTP also it can use, HTTP 1, HTTP 2, like whatever it wants to use, it can use, right? So there is no restriction. It's not that as soon as you are making an HTTP call, it has to be REST. No, that's what basically that's where gRPC comes into the, or basically that's where RPC comes into the picture. It can use any application level protocol, HTTP 1, HTTP 2, even WebSocket. Who's stopping from implementing this over WebSockets? It's just a network call, right? So everything is pretty abstracted out. You can use WebSockets, raw TCP connections, anything to do it, right? But the idea here is RPC runtime would pick its own network or would have its own preference. For example, gRPC says I will only use HTTP2 as my transport layer. gRPC will use HTTP2 for transport. If you would want to write your own RPC, you say that I want to talk to WebSockets only. You can very well do that. No one's stopping you from doing that, right? But that's where we need to understand that the transport is totally separate, and the way we would want to communicate, it's all abstracted out using gRPC. Okay, now let's go through the final section of it. Why RPC, right? Why did this thing suddenly revive itself after 10 years? Okay, so why remote procedure calls? You would have seen the core highlight of this is that it's very easy to use because it makes a remote function call just like normal routine local procedure call. It gives you this native classes to play with, which is generated by your own interface definition. So you don't have to write the code again into multiple languages. It gives you strong API contract. Like for example, what you typically, let's take an example of REST. You wrote a request, you fired a request, you got a response. Someone added a new field in the response. You need to explicitly handle that. Why can't this be done automatically through native objects? Why do you want to like JSON, you got it and you convert it into your native objects and then you use it and then you would want to make the changes there? Why do you want to fall into such complications doing that same serialization, deserialization again and again? Abstracting it out is the best way to do it. So now with RPC, what you get is you get very strong API context. You exactly know what you are sending. You exactly know what you are getting. No matter how many iterations happen, you would know what you are signing up for. Right. Second is invoking a remote call is just like a local, it's just like a local function call. So it boosts massive dev productivity. You don't have to worry about making a request.post and then you pass the URL and then you send it and whatnot. It's all abstracted out with the stubs that you generate. So it massively boosts the overall developer productivity. And you can actually ship things much faster in a much efficient way. Third, most RPC framework like gRPC supports modern languages. So for example, you define the proto file in, you define your interface definition in your proto file. You can create Golang code out of it, Java code out of it, C++ code out of it, Node.js. Pick your favorite language. Like most modern RPC framework supports all modern languages. So which means that if you pick an RPC system, you can create code for all the languages out there. You don't have to write it. It's auto-generated. Best part, you don't have to do that mundane task of doing the serialization and deserialization again and again. It's all auto-generated. Then, most mundane tasks are abstracted. For example, failures, retries, payload conversion to native objects. Like for example, you send JSON and then it needs to convert it into that native object so that you can use it. All of that is abstracted. You don't have to worry about it at all, right? Mundane tasks are abstracted and the network protocol is abstracted. Multiplexing is done. You don't have to worry about those stuff anymore. It's the RPC system that takes care of it, right? You get performance out of the box. For example, compression of payloads, you get basically connection pooling because you can have raw TCP connection established, you can do connection pooling, gives you massive performance gain. You can do multiplexing, you can do streaming, you can do efficient payload transfer. Just like compression, you can apply some advanced or plus with the format in which it is sent, you can very well define a very compressed format. Like for example, protobuf itself is highly compressed format in sending it. You get efficiency out of the box. Then security is just a plug because here with RPC, with inter-service communication, your security itself can be abstracted. For example, HTTPS based communication over network needs to be encrypted even though it is inter-service communication. You can very easily do that. Just configure it at your RPC level. You don't have to do it on every single HTTP request that you are making. Here, it's all abstracted in this one RPC system. And another big advantage, which is why you would see most of the companies that offer APIs or they expose APIs, they typically expose, good companies expose it in RPC format. So what they do, like they expose HTTP endpoints, but behind the scenes they have RPCs. So what happens is that you don't need to write client libraries. You saw we have protofiles. Protofiles create stubs for multiple languages. This way, if you have a gRPC or if you have an RPC server, you can just ask or your client can directly connect with can directly talk to this RPC server. And with that, the protofile that you have can generate your client libraries for you. For example, a great example of that is Slack's API. Slack's API are all RPC based. They are HTTP endpoints, but they are RPC based. So you would see they have a very different way of defining endpoints, and that is because they are RPC based. So now any Slack client that you see in Golang, Python, Java, they are all auto-generated. They don't need to spend time writing the code for that client any time something changes. It's all definition based. Big advantage. And here another solid advantage that you get is multi-language communication. For example, Golang struct, Java classes, they want to talk to each other. Doing it via common JSON, serializing and deserializing. Why do you want to put that effort? RPC abstracts it out for you. Massive advantages that you get by using RPC. Now obviously, grass is not always green. What are the concerns while using RPC? So stubs needs to be regenerated whenever the signature changes. This is one big thing that you always have to think about, that if let's say you defined your protofile with some methods and some members in it, you change something. Now this change needs to be percolated on both the services, for example, authentication service and notification service. So whenever something changes on the stub, everything needs to be redeployed. But that is still okay because you don't have to, it's just generator who would do that part, but still you would have to redeploy your service. Right? Was first concern. Second is testing RPC is non-trivial. It's not difficult, but it is not intuitive also. So writing test suites for RPC, it looks simple, but you just need to be wary of the fact that it is a remote call. You might need to test on few edge cases, and it becomes, for a normal developer in a day-to-day life, transitioning from REST to RPC might feel a little weird. Third is getting started is a little challenging because unlike REST, where you just start a HTTP server, start exposing endpoints with basically resource-based endpoints and done. With RPC, you have to write an interface definition in a proto file, create, basically generate the stubs, then integrate it, and then implement it, and all. It takes some time to do it, right? And then the fourth one, browser support is limited. Not all browsers supports RPC, so that's why your JavaScript to server communication will happen over HTTP. Like it could look behind the scene, you can implement an RPC server, but it would not be a pure RPC communication. It will be a normal REST in not REST, but normal HTTP function invoked. Internally, it might get converted into RPC and do that part, but pure RPC implementation. So what benefits you get out of RPC in general, you might not see from your client or from your JavaScript client or from your browser to your server. But within server, so inter-service communication will be seamless when you go for RPC. This does not mean you always have to use RPC. You have to pick your battles. If you have expertise, do that. If you don't, then skip it. Right? So yeah, that's it for this one. I hope you learned something amazing with RPC. So I found a bunch of myths floating around. That's why I thought, let me do a very clear deep dive on RPC, what RPCs are, why are they used. Now you would have a very clear idea about it. What I've also done is you can visit my GitHub. I very recently created a very simple RPC hello world in Golang, which implements an advanced shellcode. I'll just link it. It's a very basic code base, but you would understand where the difference lies, right? And how to basically implement it. So what I would highly encourage you to do is I would highly encourage you to implement a hello world in gRPC. gRPC is the most famous one out there. Just implement a hello world. You will understand far more than just going through some theoretical shit. So just write a basic hello world of gRPC and see the beauty of it. Like you done, like if you have used REST, then you use gRPC, you'll understand how much simple gRPC makes. Obviously, getting started is a little challenging, but it's worth the efforts, to be really honest. Right? Chala. That's it for this one. I hope you guys, if you guys like this video, rather, it's a very intense deep dive, but if you guys like this video, give this video a massive thumbs up. If you guys like the channel, give this channel a sub. I post 3 in-depth engineering videos every week, and I'll see you in the next one. Thanks a ton.